Hi there, how's it going? Time for another engineering mechanics problem. So let's get straight into the problem. Okay, so in this problem we have a dump truck, has a load in it. We're told that the weight of the dumpster plus its load is 25 kilonewtons. So you can see that up here, and it acts through its center of gravity here, G. And it's supported by pins at A, so probably more than just one. There might be one on each side of the dumpster, and it's also supported by this hydraulic cylinder BC here. So we're asked to determine the force in the cylinder BC. So what force do we need to have in this cylinder to keep the dumpster and its load in this location? And also what is the force in the pins here at A? Okay, so we'll just calculate the total force required, and then if you're doing a design problem, then you'd need to design, well, do we need 2 pins or hinges? Do we need 4? Whatever. So, but we'll just work out the total reaction force there. Also, you know, that if this was a design problem rather than just an analysis problem that we're given at the moment, you know, given that you've designed the dumpster here, and you want to carry a certain load, it might be 2 ton, 10 ton, whatever. So then once you've done that, you would need to size your hydraulic cylinder here and the pump for the hydraulics and so on. Okay, so that gives you a reason for why we're doing this problem. Okay, so a lot of engineering mechanics textbook problems, they tell you to do stuff like calculate forces, but they don't tell you why. And if this was a design problem, then that would be the reason for calculating these things. All right, so let's get started on the problem. So just go on to the next page here, and we start by drawing our free body diagram. So I didn't write down the solution plan, as I sometimes do in some of my other videos. You'll see the solution plan, but usually the same 4 steps. Right? So you draw your free body diagram, you then write your equations of equilibrium, and you use the unknowns that you've indicated on your free body diagram in those equations to solve for those unknowns. So that's the 3rd step, solving for the unknowns. And then the 4th step is thinking about your solution and doing some checks to just try and give you a bit of confidence that you haven't made any silly mistakes anywhere. All right, so we've got our free body diagram shown there now. So in this one, it can just be a simple rectangle. And as I always say, make your free body diagrams relatively large, but importantly, make them neat. Make it easy for you to be able to see where the important features are. Right, so you can easily see the dimensions and where they go to. Okay, so I see a lot of students don't take enough care with drawing their free body diagrams. And, you know, they'll have this dimension here, 3, you know, might be off to the left of A or off to the right of A. It doesn't actually go to point A. So just be careful and make sure you clearly communicate what your solution is. Okay? You know, part of engineering, or a large part of engineering, is communicating technically and correctly. Okay? So get into the habit of always doing this. Okay, so we can start adding in our forces now and or moments, if there are any applied moments. So usually start with the loads that we're given. Okay, so we're told that the weight of this dumpster acts through its center of gravity here. Right, so we can put that in and label it as W. Okay, so in drawing our free body diagram, we've removed our things that are attached to it. So there's other components that are attached to it. So the main frame of the truck, so we've removed that, and we've also removed the hydraulic cylinder. So what we need to do now is to show on our free body diagram the forces of interaction, or forces and or moments of interaction between those connections. Okay, so what is the hydraulic cylinder exerting on the dumpster? What is the bed of the truck exerting on the dumpster at point A? One thing that we need to note, and it's fairly obvious in this problem because remember, this hydraulic cylinder is straight, but we need to recognize the fact that this component BC, the hydraulic cylinder, is a two-force member in equilibrium. Right? So that's very important to note that, because what that tells us is the direction of the force here at B. Okay? Without recognizing the two-force member, we would have to draw force and an unknown angle, or more usually two components of force, right? And that would be two unknowns. When we get down here to point A, right, that's also a pin connection, so that will also have two unknowns, right? Either a force and its direction, or two components. Okay, so because we know that this hydraulic cylinder is a two-force member in equilibrium, we know that the force at C and the force at B must be equal and opposite, and along the line joining BC, right, we know the direction of that force there. So we can start to put that in. Right, so I've indicated that angle is 50 from the bottom of this dumpster. And we can see that because we've got 20 here, 30 here. This angle here will be, 140? Okay, so this alternate angle, I think that's what you call it, here will be 50, okay? So you know that this angle out here will be equal to those two angles on the inside of your triangle there. Right. However you work that out, it's fine, doesn't matter how you work it out. You could also indicate the angle that this is from the perpendicular to the dumpster, if you like, but I'm thinking ahead to how I'm going to solve this problem, and I've just indicated this angle here is 50 from the base of the truck, right, or the dumpster. Right, so now that we can done that, we can put in our force. I've already put in the sense of that force, but I think you should be able to work that out yourselves pretty well by now. So if we took moments about point A here, this force here, G, is acting downwards. Right, so therefore that's causing a clockwise moment about point A. So therefore this force here has to be pushing up to cause an anti-clockwise moment about A for it to be in equilibrium. Okay, so then we can now go and look at point A. And what I'm going to do is, instead of using our usual horizontal and vertical XY components, I'm going to find components that are tangent and normal to this bottom of the tray, or bottom of the dumpster here. So T here is along this line, parallel to the bottom of the dumpster, and N is normal. Right? And the reason I've decided to do it that way is because I've been given all of these dimensions here, right, along the length of the dumpster. Okay, so I know that I'm going to have to use moment equation, right, and calculate the moments of various things. So I've decided to find my components in this orientation. Now you could do it using X and Y, horizontal and vertical. In fact, why don't you have a go at that for yourself and see if you get the same answer. And with all of these problems, it's probably a good idea that you have a go at them yourself first, get as far as you can, and then stop, come back to the video and have a look and see how I did it and compare it with your solution. Okay, so I put on my reactions there. We can try and think through whether these are positive, that the sense of these should be in these positive directions or not. So the horizontal one, I think we can see, yeah, that's going to need to be up to the right because we've got these components all pushing down to the left. And this one up here, so we've got the weight here as our main load. So most likely this is going to need to be pushing upwards. Okay, so they're probably the right sense. We'll see as we go through our calculations whether that was correct or not. Okay, so label our unknowns. So FCB for the force in the cylinder BC, and the reaction forces at A, call them RAN and RAT, right? Indicating that we're using that normal and tangential coordinate system. So now here I've just broken this weight force up into its component forces in the normal and tangential directions. Okay, so I'll need to do a bit of trigonometry here and geometry to work out the correct angles and whether I use sine and cos for this normal component here or this tangential direction component. Same with my force here. I've drawn component normal or perpendicular to this bottom of the dumpster, right? So in the normal direction, and I've got one in the tangential direction. Okay, so as usual, when we're doing equilibrium problems like this, it's usually most convenient to start with a moment equation, because we can usually work out a location to take moments about that enables us to find one of our unknowns straight away. Okay, and usually if we've got a pin connection like this, where one of our unknowns are, the components of these, of the force here, both pass through point A. So therefore they'll have zero moment about point A, and we'll just be left with the force FCB and its moment action in this equation. Right, so we write our equation, sum off the moments about point A, and again, I point out that it's very important to have this point A here, right? Because when we look at our equation that you've written, that we write, we need to have this in order to be able to interpret or check what you're doing in this next line that we write. Okay, so it's in equilibrium, so everything is equal to zero. So now we can start looking at our terms. So I started here with FCB sine 50. So can you see which one that is? Will that be this component or will it be this component? Okay, the normal component or the tangential? Right, so if you look at this angle here, 50, this is our triangle. This is our triangle here that we're using for Pythagoras. Then this here is the opposite side, which is the same length as here. Okay, and just I point out that when I draw my components, I always draw them like I've shown here, right? So that the correct line of action of the components is maintained. Right? So what you'll see some people do, if I just quickly do that, right, is to draw that component out there like that. So they draw their components like this, right? Which is not strictly wrong, right? But what it does do is lead to, it's a bit misleading, right? Because if you've got your component shown out here, then you're looking for, when you're doing the moment calculation, right, you're looking for the distance between this component here and point A, right? So if you've drawn it out here, right, you're looking for the distance from here to here, potentially, right? So try to get in, if you're into the habit of drawing your components like this always, without thinking about what you're doing, try to stop yourself from doing that and start to try and draw your components like I have here, okay? So you maintain the correct line of action of your components. All right, so let's get rid of those of my drawing. Okay, so it's going to be this component here, because this one, right, is the adjacent component, will be FCB cos 50, right, and that is tangential to, in the tangential direction, located at B, so it passes through point A. So it's going to have zero moment effect. Okay, so FCB cos 50 will have zero moment. All right, so the other thing we need to check for now is whether this is positive or negative moment. So if this is pushing up here, then this will tend to rotate this dumpster around anti-clockwise. Okay, so that'll be a positive moment. All right, the next one. Oh, sorry, we need to put in that distance first. Okay, so the distance from this force here down to A is 3 plus 1. Okay, so that's what's given for us over here in our question. All right, so then we have the weight force. Now, we have to find the components again, right? Because this force is not in this normal direction, right? It's at an angle to the normal and tangential components. Right? And hopefully you can see that the angle in here will be 20 degrees. Right? That's just another reason for drawing your free body diagrams large, neat and clear, because your angles look kind of right and it helps you to do your trigonometry and geometry correctly. The angle here is 20 in here. So if we're using W sine 20, which of these components are we using? It's this tangential component. Okay? Because the 20 degrees will be in here and this will be the opposite side of the little triangle. Okay, so that force here, its perpendicular distance to point A. Right, so if we continue that line of action down here, we continue this line of action, its perpendicular distance to point A is 1.5, okay, which is what we've got on our drawing up here. Okay, so hopefully now you can see why I made the choice to use these components or these coordinate systems rather than horizontal X and Y, because I've got all these dimensions already. You know, you can use your angles and trigonometry to work out the horizontal and vertical distances if you like. Should give you the same answer. All right, so let's have a look here and see whether it's a positive moment or not. So this is going down this way. So this will tend to cause an anti-clockwise moment about point A. So this one will be positive as well. Then we also need to include this normal component here. And so that will be W cos 20 times its perpendicular distance, which is given for us here, 3. Okay, so we can put that in, W cos 20 times 3, and is that positive or negative moment? Let's have a look. So this normal component here will be pushing around this way. About point A, it will cause that component to rotate clockwise around point A. So this is going to be a negative moment in that equation. Okay, so that's all of our forces causing moments acting on this body. So we can put that all equal to 0. And now we've got one equation and one unknown, which is our hydraulic cylinder force FCB. All right, so do the algebra and rearrange the equation. I've done a longhand there so you can see that, and you can then do your calcs to work out the reaction force. Oops, I forgot to put a stop in my solution there. Anyway, the next part's the easier bit usually. So the next two equations that we have to use are the sum of the forces. So we've used this normal and tangential component or coordinate system. So if you sum the forces in the normal direction equals 0, indicate which is the positive sense. Right, so we can start from left to right. So we've got RAN up here at A. It's going in the positive direction or positive sense. Then we have the normal component of this weight force that's acting. Okay, so we saw that that was W cos 20, and that's in the negative direction. So we can see we've got negative here. And then we've got the normal component of FCB, and we saw that was FCB sine 50, and that's all equal to 0. So you can rearrange the equation and solve for RAN. Okay, so next up will be some of the forces in the tangential direction, okay, indicating upwards to the right as positive. And so we've got our reaction component here, RA subscript T, going in the positive direction. And then we have our weight force, right, or the tangential component. So this one up here. So that was W sine 20. And then we have this one here, this component tangential. That's the adjacent side to the 50 here. So FB cos 50, and that's acting in the negative direction. No other forces, so put that all equal to 0 and do your algebra and solve for RAT equals 20.64 kilonewtons. Just repeating those on our next page for reference. So if you want to find the magnitude of that force, so if this is a design problem, you want to know what the total magnitude of the force acting on that pin is, so you can select the right material and size for that pin. Okay, so you should know just square root of sum of the squares to do that. So let's check our solution. I've just redrawn for you here the free body diagram. So what I've used here, just because it's in the subject that I'm teaching, that we're looking at 2 and 3 force members. So usually two force members are much more important, and you use those much more often in solving problems like this. 3 force members were really useful when if you did engineering studies in high school, you might have done graphical methods, and then using 3 force members, or identifying a 3 force member and using its properties in your graphical method made the solution easier. Okay, but typically we don't do graphical methods when you get to university in practice, but they're still important to know about when you're doing your analysis. All right, so if we have a 3 force member in equilibrium, therefore we know that all 3 forces are concurrent, which means that they all pass through a single point. Okay, all lines of action of the 3 forces pass through a single point. Now you may be looking at this free body diagram and thinking, hang on a second, there's 4 forces here, right? But remember that we've just up here turned these 2 components into a single resultant force. Okay, so we have a single resultant force RA, the weight, and the hydraulic cylinder force FCB. All right, so if we continue the line of action of this force, it will pass through the line of action of the weight, and then we know that the resultant reaction force at A must pass through that point of intersection. Okay, so we can put that on our diagram like that. So then we can also just do some simple checks to think about, well, what's our solution doing, without really doing any calculations. Have we got the right order of magnitude of things? So we can have a look at this and say, all right, we've got in our solution, RAT is greater than RAN. Right? Does that make sense? Right? If we go now and look at our 3 force member diagram here, where we've got the directions of our forces now, we can see that the line of action of this resultant force is going to be much closer to the tangential direction. Right? This angle here is smaller than the angle on this side, so therefore our component RAT must be greater than the component RAN. Okay, so that gives us just a quick little check to see that we've got this not wrong. This check is not going to tell you that you've got it right. Okay, but hopefully it will identify for you whether you got something wrong somewhere, right? So you might have had sine and cos the wrong way around, or you might have used a wrong angle, whatever. Okay, and then the other thing you can do with your 3 force member diagram is because we've got 3 forces in equilibrium, they will make a closed triangle. So we can put in our weight force here, acting down, our reaction force, or our hydraulic cylinder force, FCB, acting at 50 degrees. We can put in that dimension, and then we know that the force that goes from here to here must close that triangle. So I just put in here my justification, sum of the forces equals 0. So RA goes here to close that triangle. All right, so this 60 here, so you'll need to do a little bit of trigonometry to work out why this is 60. I'll leave that for you to do. And then if we use our cosine rule, we can check for our value for RA, and we get the same value. Okay, so that's kind of using some of the answers that we've got. It's kind of like substituting our values that we've just calculated back into some other equation. So if we redo, another way we could check would be to take moments about point B here. Okay? And in fact, we could have done that in our first moment equation in this instance, right? Because RAT passes through point B, right? We would have found RAN straight away. Right? It would have been still one equation and one unknown if we'd taken moments about point B. Right? So again, that's another exercise for you to do. Just go back and do that. Right? Start the problem again, right? And take moments about point B instead of point A and solve for your unknowns. Okay, so then at the end, just write down our final answers, round up to 3 significant figures. And yeah, so hopefully that was helpful for you and a bit more of a realistic problem than you may have seen in some of the other things that you've done. All right, so good luck with your studies, and I'll see you in the next video. Bye for now.